Okay, well, thank you folks for giving me the opportunity to tell you about some of the work that I've been able to be involved with over the last couple of decades, as it were. I'm going to very briefly give you an overview of various things that are ongoing in my group, because I won't have time to cover the various topics in detail. I like to think of the fact that I have a profession. The profession is in the area of nonlinear optics. It's an area that is concerned with the interaction of light with materials. It can be used for a variety of things. It can be used for optical switching. It can be used for 3D imaging, 3D microfabrication. And so what I like to think that we've been able to do is take these equations that have been given to us by physicists and theorists, which describe nonlinear optical phenomena in terms of transition dipole moments and resonant energies, which looks a lot like gobbledygook here, and then translate that into pretty simple structure property relationships which guide chemists to make molecules that can be effective for things like 3D microfabrication, which is now used commercially, as well as a process that's referred to as all-optical switching. And so we've been working on materials that are organic, and in this case organometallic, that turn out to have very large optical nonlinearities, as it turns out very low two-photon absorption, and good linear loss. And we're now at the point where we have materials that we can sensibly consider for all optical switching. And the reason that people are interested in that is that we are demanding more and more bandwidth every day, and that requires very, very high-speed data processing. These are the types of materials that can be used for that. So this is the area that I know best, and I'm not going to talk about. Then I have what I consider to be a relatively serious hobby, and that's organic electronics. I've been working in that long enough that it should be more than a hobby. It's about 20 years. And our group's been involved in the development of organic semiconductors. We focus more on what are referred to as electron transport materials and hole transport materials. And as the name would imply, these materials transport electrons more efficiently than they transport holes. We are working on materials that are dopants. These are materials that can be used to either oxidize or reduce materials, and I'll explain to you why we're working on that. And then we're working on various different ways to make these materials more cleanly using CH functionalization. And I would have to say that we are not people who are developing CH functionalization chemistry. We're part of a very large NSF-funded center on that. But we are people who are trying to see how it can be used in the area of organic materials to make materials that will be of relevance for optoelectronic and electronic applications in a manner that requires fewer steps. And so these are just some examples of the kinds of reactions that you can take. This is a standard building block in organic electronics. And this just shows how in pretty high yield you can just go straight from a CH bond and make a variety of diaryls substituted by diazoles with these fluorine groups on here. And these types of things are used for electron transport and two-photon absorption. It can be done with cyano groups and things like that as well. And this all can be done in very, very high yield, sufficiently high yield, that one can think about making polymers using this chemistry. And we're working on that, and we're working collaboratively. The last area of interest for my group is surface chemistry, and I very carefully use the word surface chemistry as opposed to surface science, because I think there are people who really know how to study and characterize surfaces, and I would not put myself in that category. But I know how to do some organic chemistry that can modify the properties of surfaces, and I know how to work with people who know how to basically characterize things pretty well. And so in this area, we've been involved in developing something which is called thermochemical nanolithography. It's a very simple technique. It's a technique where you take an AFM tip and you can heat it between room temperature and 1,000 degrees. You can cycle it 10 to the 7th times per second between these two temperatures. And if you drag it across the surface, not surprisingly, you can do thermally activated chemistry, but maybe a little more surprisingly, you can do that with a pretty high degree of selectivity with a resolution down to about 12 nanometers. Okay? And so this is a very simple way of doing nanopatterning. This is a cartoon of taking graphene oxide back down to reduce graphene, and it can be done in air with, as I say, a precision down to 12 nanometers. We also work on modifying the properties of surfaces, and in particular what I'll focus today is on modifying the work function of materials. And this work function is something that relates to the ease with which you can inject or collect electrons or holes by tuning the energetic energy of the material relative to the HOMO and LUMO levels of molecules. And when those are well aligned, you have a very low barrier to overcome to inject or collect electrons or holes. And when they're not, you have to do work. You have to apply a potential to do that. So we are playing around with different approaches. As is often the case when you get to be my age, I've done none of the work. I simply get up and take credit for the work that people have done. I've become pretty good at doing that. And, but I am very fortunate to work with a group of very talented people in my group who have synthesized a lot of the materials that we're working on. I've also been able to work with Bernard Kipelin at Georgia Tech, Jean-Luc Breda at Kaus, and then Sam Graham, who's in mechanical engineering, and then this is Antoine Kahn, who does beautiful work using photoelectron spectroscopy, in particular UPS and IPES, inverse photoemission spectroscopy, that allows us to characterize the electron affinities and the ionization potentials. A variety of different folks have funded this, and we're very grateful to them to enable us to do the work. So getting down to business, our work is focused on doping, or at least the aspect of the work that we're going to talk today about is focusing on doping. The area of doping organic materials goes back an awful long way. And indeed, Alan Heeger and Hideki Shirakawa and Alan McDermott all shared a Nobel Prize for this. But in the area of organic semiconducting materials and devices, one of the people who really did a lot of seminal work was a guy named Carl Neo at the University of Dresden. And Carl has founded 2 companies predicated on this. He's a physicist. The company develops materials, but there are very few people in the chemistry community developing dopants. I don't fully understand why, because I think that Carl and others have really shown the value of these materials for organic chemistry. Carl wrote a very nice review in Chemical Reviews, and I'm just kind of taking a few things that he pointed out in this review that are reasons why we may be interested in using dopants. So they can obviously lead to an increase in conductivity by inducing charge carriers, but they can also fill traps, and these traps impede conductivity and mobility, as I'll show a little bit later. They can also lead to efficient charge carrier injection in a variety of different ways, predominantly by, I would say, tuning the work function of the materials such that that work function is aligned with the frontier molecular orbitals into which you're either going to inject or remove an electron. And that can be used for a variety of applications. Organic light emitting diodes use them, photovoltaics, organic field effect transistors. So let's consider the area of things that are endopants, i.e. things that inject electrons into materials. So there are things that are being used for organic field effect transistors, and those things are typically very, very easy to reduce. So things like TC&Q is used in that regard. And these things, if you look at them raw, they'll be reduced to the radical anion, and that's not very challenging. As you go up to the area for organic photovoltaics, things like carbon-60 and perylene diamides and naphthalene diamides, those are still pretty easy to reduce in the grand scheme of things, but you're getting to the point where the radical anions of these things can react with water and oxygen. And then as you go into the area of organic light-emitting diodes, if you want to create blue light, you need to put an electron and a hole on a material with sufficient energy that the photon that's emitted is in the blue. As a consequence, the electron affinity of these materials is relatively low, and the ionization potential is relatively high. In other words, they're pretty hard to reduce and pretty hard to oxidize. And so if we want to dope the kinds of materials that we end up wanting to use to make organic light-emitting diodes, and for example, get very efficient charge injection, those things require very, very strong dopants. Things that are themselves typically highly air-sensitive materials. And so it turns out that people would like to have things that were very strong dopants, but relatively air-stable so you can handle them. And that's a bit of an oxymoron. Okay? So we were thinking about how to do that. And we were thinking about the properties that we want of a dopant. We want very good electron transfer. We want the doping to be spatially localized. We want the ions to be trapped. We want to be able to use them in vapor solution and vacuum deposition, which imparts certain things about their volatility and their solubility. And as I said, you want to be able to handle them. Well, the way we got involved with this was as a favor to Antoine Hahn, who wanted to be able to reduce things. And he asked us, well, what can we use? And as a person who is trained in organometallic chemistry, it's very obvious what you would think to use. The very first compounds that I would say were very well studied in organometallic chemistry are metallocene. Everyone knows that ferrocene is an 18-electron compound. And that if you go just to the right of ferrocene and look at cobaltocene, it's a 19-electron compound. That 19th electron is putting into an antibonding orbital, and as a consequence, it is highly destabilized, and it's a strong reducing agent, and it's also rather air sensitive. Okay? And you can go from cobaltocene to decamethylcobaltocene. These compounds are commercially available. I will note that once you oxidize cobaltocene to cobaltocinium, the cation is an 18-electron compound that's very stable. But these things are very air sensitive, and for vacuum deposition, it turns out that they're too volatile. So once you use them in a high vacuum chamber, it turns out that unless you bake out your vacuum chamber for about a week, every single thing that you put in afterwards is going to end up being doped by this material, and the people who use those kinds of systems do not find that nearly as entertaining as I just did. So that was a bit of a problem. Whatever the case, you can dope things very effectively with this, but it's not as strong as you'd like for certain applications. Well, Carl Leo reported the fact that a leuco dye, the leuco dye from crystal violet, which is this compound with the H there, actually dopes C60, and what they speculated is the mechanism by which it dopes is first an uphill electron transfer to give C60 radical anion and a radical cation of this dye, and then this interacts with the C60, and there's a hydrogen transfer, okay, and you end up with a mixture of C60 minus and C60H of some form. Now, for people who work in the electronics industry, I can tell you that you spend an awful lot of time to work with pure materials. And so if you have a process, by definition, gives you what you want and some other stuff that you don't want, that doesn't seem like a great idea, at least to me. Okay? There are other examples of this, one done by my good friend and collaborator, Jean Bao at Stanford, and it basically works actually. Doesn't even work like that. This works like sodium borohydride. This is an H- donor. Speaking of isotope effects, you can determine that by looking at the primary isotope effect of the kinetics. And it basically makes C60H-, which then goes and transfers an electron to C60H, and you end up with this mixture. Well, we thought that there might be a better approach. And the better approach that we thought was, if you imagine this, and you replace that by a second equivalent of the large organic, if you replace the H and you made a dimer, then you would have no hydrogen to transfer. And in the context of looking at the metallocenes, that would translate to having something like cobaltocene as a dimer. Well, it turns out that cobaltocene doesn't form a dimer, but that if you go one down in the periodic table from cobaltocene to rhodocene, that it was known back in 1966 that if you reduce rhodocinium, okay, you generate transiently rhodocine, but that is not stable at ambient temperature. It dimerizes to give you this material. And the interesting thing about this material is that it is actually an air-stable material. We isolate it in air, you can wash it in air, okay, and you can manipulate it in air. But if you react it, it reacts a lot like it was that, okay? And indeed, if you sublime it and isolate stuff at 77 Kelvin, you can isolate and observe this, and if you warm that back up, it goes to this. Another interesting thing about this material is that if you do the electrochemistry of this material, okay, and you don't do very, very high-speed scanning, when you take this material and oxidize the dimer, what you end up isolating is the cation. In other words, once you make the radical cation of the dimer, it very rapidly falls apart to a cation and the 19-electron species, which under the potential of the oxidation instantaneously goes to the cation. So as it turns out, there are quite a few of these materials known in the rhenium series, and we're just making these, in the iron series, and we've made a bunch of these guys, and in the rhodium and iridium series, and we've made quite a few of these guys. And we've asked ourselves, are these things effective as doping agents? And the answer is that they're very effective as doping agents. And I will just mention to you that a compound that's often used in organic electronics is a compound that's referred to as TIPS pentacene. It's an organic semiconductor. It is a hole transport material, which means that typically holes are injected in it. But it turns out that you can inject electrons into that material to make the anion. We know that because we've isolated it and have a crystal structure of it. And it actually turns on that you can make the dianion of this. These are non-trivial to make, but you can make them. And some of these compounds can take TIPS pentacene to dianions. Okay? So there are two mechanisms by which this can work. One is the thing that motivated us to do this, which is we have a dimer, and it cleaves to give the 19-electron compound. And then in a second, very rapid step, that is oxidized by an acceptor. And you get two equivalents of the cation of the metallocene and the anion of the acceptor. The other mechanism is the one that's more analogous to what Carleo talked about, and is the one that you see in the electrochemistry, where in an uphill step, you get electron transfer to the acceptor, and then you make a radical cation and an anion, and then that rapidly cleaves, and then the 19-electron compound is immediately trapped by a second equivalent of the acceptor, and that gives you what you want. Well, for reasons that are perhaps due to my heritage as a mechanistic organometallic chemist, but also because we want to design better materials, we decided that we wanted to understand the mechanism. And in two slides, I'm going to show you the product of about 2 man-years of work without showing you how we did this. But I will point out that if you consider the mechanism of first association to a monomer followed by electron transfer or electron transfer to a dimer, you can do what's called a crossover experiment. And a crossover experiment is, imagine that you had those two materials and you label one dimer red, red, and another dimer blue, blue. And then if you heat them and they fall apart, they can come together red, red, they can come together blue, blue, but they can also come together red, blue, and blue, red. That's a crossover experiment, and using a series of careful deuterium labeling studies and looking at nuclear Overhauser effects in the NMR, we can probe for that. Okay? So the first mechanism, you would expect to see that. The second mechanism, it's possible that you might see that, but if it never cleaves, okay, in the process, then you don't have to see it. Okay? Now the rate laws of these two things are going to be different. One's not going to show a dependence on the acceptor, the other one is. So one's going to be first order, the second one's going to be second order. One will not show a dependence on the driving force for electron transfer because the rate limiting step is cleavage. The other one will. Okay? And one will show a positive entropy of activation and the other ones will show a negative entropy of activation. So you can sort all this out by doing a tremendous amount of kinetics and temperature-dependent kinetics, as well as labeling studies. And the bottom line is that we can identify which compounds go by which mechanism. Okay? And it turns out that the rhodium compounds go by a cleavage mechanism, and a lot of the other compounds go, in fact, by the electron transfer mechanism. And it turns out that, for example, this particular rhodium compound, actually both mechanisms go simultaneously. And you can see that in the kinetics. Now, why is that relevant? If you think about the thermodynamics for this process, and you want to make stronger and stronger dopants, you need to ask yourself about what is the free energy for the entire process of going from dimer plus 2 acceptors to 2 cations and 2 anions. And so I've talked about the fact that these are strong reducing agents as the 19 electron species. And so if we started at these 19 electron compounds, then we could simply look at the oxidation potential of those and have a sense of what's going on. But we're actually stabilizing these by forming a bond. And so we first have to cleave that bond, okay? And then we can have the reducing agent. So to understand what's going on in terms of how strong these materials are as reducing agents, we need to essentially take this oxidation potential and subtract from that half of the bond strength. Okay? Well, so it turns out that if we look at the oxidation potential of the 19 electron species, some of the compounds look a lot better than our rhodium compounds. So we think, now that's great. These should be more effective reducing agents. But unfortunately, those compounds all go by the second mechanism when there's electron transfer, followed by cleavage. And the reason that they do that is because the carbon-carbon bond is strong. So we have a chart here that shows what the oxidation potential for the dimer is, what the oxidation potential for the 19 electron compound is, and then what the effective oxidation potential for doing the reaction is. And what you can see is that while these compounds look really good, when we look at their effective oxidation potential, due to the increased bond strength, they drop a lot. Whereas the rhodium compound drops very little because it has an intrinsically weak bond. And we can measure that, and we've used theory to calculate that. So we reasoned that if we want to make a stronger reducing agent, we're going to have a hard time making the ruthenium compound, the rhodium compound, much stronger because we've already kind of put a lot of inductively donating groups on it. So what we have to do is perhaps think about a way to make the bond in these other compounds weaker and take advantage of the fact that the 19 electron compounds are intrinsically more reducing. So again, we go to sophomore organic chemistry. And if you're a sophomore organic chemist and you want to make a weak single bond, how would you do that? Well, it doesn't take the logic of Spock to know that cyclopropanes and cyclobutanes are highly strained. So what we did is we started out with a cation that was made from a cyclophane. Okay? And then we reduced that, and by virtue of the fact that the geometry is constrained to have these two carbons right on top of each other, you can isolate a compound with a strained 4-membered ring. And as you know, the ring strain in these things is on the order of like 23 kcal per mole, and so that gives you a driving force. Now, we have not yet isolated or determined what the thermodynamic driving force is. But what I can say is that when we examine this material versus the compound that is roughly analogous, that doesn't have the strained ring, it goes much, much more quickly as a reducing agent. Okay? And so we suspect that we are now, with this kind of material, making reducing agents that are substantially stronger, yet air stable. The reason that this is relevant is that these materials are right at the cusp of what's required to reduce acceptors for OLEDs. And so we are kind of within 0.2 volts of being where we need to be to reduce the kinds of materials that people want to use today in these applications. So now, actually, what we're going to do, we're working with companies. There's a company in England called Cambridge Display Technology, and we're working with these things to begin to evaluate their efficacy in organic lighting evaluators. Let me tell you a little bit about what these things can be used for. Okay? So one of the things that you have with organic materials is the fact that they are fundamentally, even if you purify them, relative to inorganic semiconductors, they're very, very messy. They have a lot of trap states. They're never at the level of purity that you have for silicon that we use routinely. And as a consequence, for example, now we're looking at a picture where there is hopping of an electron. The electrons have the manifold of states, and then there are states that are low-lying states that are referred to as trap states. And when the electrons get into these trap states, there's a non-trivial barrier, energetic barrier, for them to get back out. And if you got those trap states filled with electrons, then the electron wouldn't have to go through them, and you could have a much higher mobility. Okay? So what you need for that is either a compound that is strong enough to reduce your molecule and the trap states, or a compound that can reduce both, but that's present only at the level that there's enough of it there to fill the trap states. Okay? And those trap state levels can be measured using careful photoelectron spectroscopy, UPS machines. So working with Antoine Kahn at Princeton, we decided to examine this for the example of carbon-60 and our ruthenium dimer. And the idea is now is we're going to mix these things at different concentrations, going from 10 to the minus 4 mole percent, which we refer to as ultra-low doping, which inorganic semiconductor people would refer to as ultra-high doping. Okay? And we're going to look at the investigation of a variety of things, some of which I'll show you here. You can look at the Fermi level versus doping. You can look at the electron transport and conductivity. So if you look at the conductivity versus doping, what you can see is that you have a regime that is linear here and then another regime that is linear there. If you look at the activation energy for doping, you have a regime that's linear here and an other regime that's linear there. I'll make two notes. One is that you can dope these things to get up to 10 Siemens per centimeter, which for electron materials that are conductors is pretty high. Okay? The second is that you have to only go up to about 10 to the minus 3 mole percent to get to the point where you go from a trap filling regime to where you're actually doping the material itself. So a tiny, tiny bit of this can be used to effectively clean up the material. Okay? So here's an application for use in field effect transistors. So you take C60, you make a field effect transistor out of stuff that you buy as, quote, reasonably pure C60, okay, which means it's ostensibly 99.9% pure. Then you take that and you sublime it another 4 or 5 times. Okay? So if you make a material out of the stuff that is supposedly pure, it has what is referred to as a very high turn-on voltage, the voltage that you need to apply to the system to get the charges to flow, and it has a measured mobility of about 0.38. If you dope it, again, at just about 10 to the minus 3 mole percent, the mobility basically doubles. And if you look at the voltage that you need to turn it on, it goes down by a factor of 3. And in fact, it basically ends up with the same voltage that you would have for using the 5 times sublime C60. So, you know, you might say, well, I just want to use 5 times sublime C60 to make a pure material. And while that's costly and so on and so forth, you could do that. But a lot of the materials that people want to use today are polymeric. And the ability to purify polymers by sublimation is simply not there. So you are going to deal with materials that have trap states. And effectively, what this is a mechanism by which you can clean up materials with a tiny, tiny amount of an air-stable dopant that end-dopes the materials and improves performance. Another thing that you can do is you can lower what's referred to as the contact resistance. So you can have a material through which you flow charge very, very easily. But if getting the charge from the electrode into the material is prohibitively expensive in terms of the energetics, then it basically makes no difference. You're going to be limited by that so-called contact resistance. And it turns out that if you simply put a couple of nanometers, 3 nanometers of the dimer, underneath your electrodes, you can drop the contact resistance quite dramatically, and that leads to an effective mobility, the speed at which the electrons move in an applied field, that goes up by about a factor of 3 to 4. You're not actually changing the material itself. You don't actually measure the mobility of the material. You measure the mobility of the material in a certain device configuration. And if your device is screwing up the behavior of your material, you can have a great material and have it still behave poorly. So this provides a way of fixing things like that. Okay? I'll briefly mention that we have p-dopants that are very, very effective. This is a compound, I like telling people about this. This is a compound that was first made in 1962 by R.B. King, and then the synthesis of it, which is shown here, was optimized by my undergraduate advisor, Alan Davis, in 1967. And the synthesis involves taking this gas, which is kind of poisonous, and then bubbling it through refluxing sulfur at 450 degrees C. So I often hear that kind of response. And as a consequence, not that many organic chemists want to do this, and I would just say very few physical chemists want to do this, and even fewer physicists want to do this. That's the perception. The reality of the situation is the way you actually do this is you take a flask, you put sulfur in, you take a sand bath, you put the material into the sand bath, and you crank up the temperature to 450 degrees. The sulfur melts and refluxes. You have a pipette, you bubble in the gas, and out the other end bubbles this little square material, which you isolate in a condenser, and then you can sublime, and that's that. So from a standpoint of actually doing it, it's no different, actually, from bubbling, I don't care what, argon through boiling water. You do it in the hood, you turn up the temperature, and you get your product in high dose. So you can make this thing, and this is a very good oxidant. It's about 0.4 of a volt more strongly oxidizing than 4-FTCNQ. I will mention that this compound is somewhat soluble. Whoops, I don't know why that happened, but because it's a Microsoft product, that's why. Let's see if I can find the thing. I'm going to ignore that and reload it. And scroll down. It's close. Come on. There we go. Let's see if this will work. If it won't work, I'll have to resort to making a PDF. There we go. You can go and replace the trifluoromethyls with a bunch of other things. It involves a different synthesis. And you can go and you can make this thing about 20 times more soluble than the other material. And that's very good for doing oxidation of materials that are meant to be solution process. Okay? People often ask, well, is this something that you can make, or is it just kind of a hypothetical thing? Do you have 2 milligrams of it? So I have a guy named Yadong Zhang, who's a spectacular guy. And the bottom line is, if you can't put it into something that's kind of something that large, he doesn't really care. So we've made this guy on 18 grams in one lot. We have these guys, and now you can go to Sigma Aldrich and you can buy these things, probably for an exorbitant price. Okay? But these things can be made on very large scale. The ruthenium compounds that I've talked about, we can make on 5-10 gram scales. And if you're using them as a dopant at a 1% or 10 to the minus 3%, you can cover an awful lot of area at 400 nanometers thick using the dopants. Okay, you can make a variety of other dopants, some of which are flat, and some of which, this is basically a bis-trigonal prism, and these can actually form charge transfer complexes with things, and these can, and that may be of relevance for certain applications. You can make what are called PIN homojunctions, and then you can make rectifiers using this by n-doping something, having an intrinsic reason, and d-doping it. Okay? You can make alternatives to using things like P.TSS as whole collection barriers for whole collection materials for solar cells. And so here is P.TSS being used in a P3HT PCBM system. Here is our material doping P3HT at 4%, and you can see it works just as well. And you might say, why might you want to do this? And the answer that I would give you is that you control the mole percent that you use, you control the polymer that you use, and it's not something that's acidic. Okay? So people are looking at that as well. If you're worried about these things moving around, you can go and make cross-linkable versions, and so we've made cross-linkable versions, and these things actually do cross-link. You can see that in the DSC. And they work quite well. If you want to link them to the surface, you can make phosphonic acids that bind to the surface that have cross-linkers, and you can go react with that. Okay. So the conclusion for this part of the talk are that these 19-electron compounds are strong dopants. They can be used in solution and then vapor processing, and they can be used for trap filling and contact doping. I want to take a couple of minutes to talk about how to modify work function. And as I said, you want to get the Fermi level or the work function of the material aligned with either the HOMO if you want to inject or collect holes, or the LUMO if you want to inject or collect electrons. You can do that by introducing at a surface a dipole. And by introducing a dipole at a surface, what that will do is it will shift the vacuum level, and that can either increase or decrease the gap for charge injection and collection. And that's pretty well understood. And so we've approached doing this using molecules that have interface dipoles. Here you can see a CF3 pointing in one direction, a fluorine pointing in the opposite direction. You can use polyethylene imine, and we had a paper out in Science, it's already 3 years ago, that shows how you can use this as a very strong Lewis base to modify the work function of things. I'll point that out. Or you can use redox active molecules. You can literally dope the surface. And if you dope the surface and you inject an electron, you will leave a cation. And that creates a huge interface dipole. So this just shows a variety of the phosphonic acids that one can use. What I can tell you is if you look, there's an arrow for where we start. It's very easy to move things in one direction. It doesn't work well to move things in the other direction. And that's because the bond that you create between the ITO and the metal oxide intrinsically is moving things up, which is good when your dipole is pointing that way, but if you're moving things up by forming a bond, then you counteract the dipole, and it doesn't work. Polyethylene imine, on the other hand, donates electrons to the surface, okay, through a variety of interactions, predominantly because it's a good Lewis base, and it can lower the work function of many things. And this paper, as an example, has been cited on the order of 300 times already. And people are just using and using and using this. Here we drink Pepsi, at Georgia Tech we drink Coke, and there we drink Dasani water. This stuff in solution to dope is cheaper than bottled water. Okay, so you can buy this by the barrel, and so everyone's using it. It works very well. You can't use it by vapor deposition though, which is important for certain applications. But you can use all dopants to dope surfaces. This just shows an example of using dopants to dope graphene. This is CVD graphene. And using the ruthenium compound or the rhodium compound and the molybdenum compound shown here, you can either fill up the valence band of the graphene or deplete the, fill up the conduction band or deplete the valence band. And when you do that, not only do you shift the occupancy, but you create large surface dipoles. And those surface dipoles tune the work function. So the Fermi level can be tuned by about 1.8 volts. Not only that, but you can affect the sheet resistance of these materials using some other dopants. And in fact, you can knock down the sheet resistance of graphene with one of these dopants from about 1,800 ohms per square to about 167. So we're now exploring the use of graphene because it's very highly transparent as an electrode. As I mentioned, you can tune the work function with these actually over 2 volts. And it works perfectly well. Okay? So we can make things that have pretty high efficiency in comparison to ITO. So we're exploring that more. It's not limited to graphene. You can dope, this is tri-layer molybdenum disulfide, another 2D material. You can move its work function by over a volt if you want. Okay? You can take ITO and you can tune its work function. Okay? And again, the way this works is that we're basically transferring an electron from the iridium to the conduction band. And then we're coating the surface with count ions to counteract the charges that are in the material. And that's just the vacuum level. And you get large shifts in the work function. This is an example that just came out last week in Nature Communications in collaboration with Robert Koch in Humboldt University, where we are doping single crystal zinc oxide, okay, grown in ultra-high vacuum. And you can take single crystals zinc oxide and take the work function from 3.7 down to 2.2 eV. For comparison, calcium has a work function of 2.8 eV, okay? So that's a huge shift, okay? And what they were able to do with this, which was of interest to them and people in the OLED industry, is they can take zinc, where they can do energy transfer to this compound, which they want to emit. But the problem is there's an offset in the energy levels, so that once you do the energy transfer, effectively you get a charge transfer of the electron back to the conduction band and quenching. So what we can do is we can take this, dope it, and shift the energy levels so that we can not only get the energy transfer, but now we tune the band offsets such that you don't get back electron transfer. And what that does is it turns on the fluorescence of this molecule. Okay? Here's another example of just showing how we can dope ITO. We can make a single layer device out of C60, and we can see, can we convert ITO from something that typically injects holes into something that injects electrons? And the simple answer is, in the absence of ITO, this flat curve is not a baseline. That is the current that you can drive through C60 without a dopant. Okay? In blue is the material with ruthenium. In red is the polyethylene imine, which is our standard. And the bottom line is that when you put the polyethylene imine, you put C60 on top of that. It's pretty comparable in terms of making ITO into an electron-injecting electrode rather than a hole-injecting electrode. I was interested in whether there are other things that can be used. There was a beautiful paper out last year on using N-heterocyclic carbines to modify gold. I don't know if people saw it, but it binds way more effectively than thiols on gold. So if you have thiols on gold and you put a carbine, you completely replace the thiols. If you put the N-heterocyclic carbine on gold and you dunk it in thiols, nothing happens. You can take those things and go from pH 2 to 11, they stay on. You can boil them in water, they stay on. So N-heterocyclic carbines are good donors, and so we were wondering if these would be effective donors for modifying the work function. And the bottom line is that the preliminary results that we have suggest that you can knock the work function of gold down to about 2.8, okay? It's still not well worked out, but it's something that we're thinking about, and then that these may be yet another tool in our toolbox to control the work function. Okay, so to actually really end, and I think I actually am on time, phosphonic acids are an easy tool to control the work function of metal oxides, but predominantly to increase the work function. The dopants can be used to either increase or decrease the work function of materials. Polyethylene imine is a spectacular material. It's dirt cheap. Anyone can use it. Okay? And we can tune the work function of things like ITO, zinc oxide, gold. We can tune graphene. We can tune carbon nanotubes. We're doing work with Mark Hirschman at Northwestern at making carbon nanotube transistors that are N-type transistors. That's going quite well. We can tune black phosphorus. I mean, fundamentally, if you can dump an electron into it, we have an air-stable material that you can play with, dump an electron into it, pop a cation on the surface. I will mention that we have cross-linkable versions of the N-dopant as well, so you can cross-link them. And we think that this is going to be a pretty robust way of modifying the electron and whole transport properties of material as well as the work function of materials. So with that, I tried not to go over. If you have any questions about this or anything related to nonlinear optics, I'd be happy to answer. But thank you very much for sitting here and taking the time to listen to what we're doing in the group.
Well, thank you very much, Seth. Let's open up the floor for discussions, questions.
So with respect to the dipole management using the fluorophenyl phosphonates, they look like there's pretty good correlation between chlorines pointing up, chlorines pointing down.
Yep.
But my fundamental question, I don't know much about this system, is there actually, I don't know how mobile it is there actually any bending in the contact between,
Very little.
or is it
Only
basically like
bend-
a solid state junction?
There's very little there. There's very little charge transfer. So if you literally transfer charge, you can get, and even in the case where we actually dope, there's very little band bending because there's such a huge density of space. Okay, most of it is just a vacuum. Most of it is a vacuum level shift. There's very little band bending.
The reason I asked is I was wondering if you saw any effect based on the, the conductivity of the arbor that you put on the phosphonate. You saw bigger effects when it was more conductive and smaller effects.
So that's actually something that folks are studying now, and I don't have enough data. What I can tell you is that there are definite effects on electron transfer rates, but I don't think that they necessarily correlate so much with band bending, but sort of just mediation of the charge transfer through the bound species. So we've made phthalocyanins, we've made perylene diamides, we've made ferrocines. In phthalocyanins, we've looked at ones that just stand up and we've looked at ones that lie flat. The ones that lie flat have 4 different things. We see much faster electron transfer rates through those, but I don't think that we've seen it so much correlate with the band bending. Yeah.
So, in your strained ring system, you incorporated being the first time.
Yeah.
You also had a linkage around the back.
Yeah.
Okay.
Which is not desirable,
Yes. Okay.
but, so here's the issue. If we, and we're working on this, but it's just not as clean. If you just have 2 things, okay, you can either form the 3-membered ring or a 4-membered ring, or you can just have 2 separate molecules come together and not form the strained ring at all, okay? But we start out with cyclophane. So you start out with cyclophane. The 2 rings are literally, they're stuck on top of each other, which means that when you make the radical on here, you've compensated the entropic cost by having the thing pre-organized to dimerize. And that's why we took that approach. Okay? But we might be able to do this under high dilution conditions, but that's why we chose to do this. We chose a system where we felt like the likelihood of us not getting garbage would be much higher. And the yield's not bad. I think it's on the order of 50%. So it works. But we've tried, the other thing that I will mention is you can make these things bulkier and bulkier, but eventually what happens is that rather than dimerizing, they'll find a hydrogen atom someplace and abstract them from solvent and just put another hydrogen on the CP ring, or the benzene ring. So we're kind of, as I said, we don't know. People are really interested in industry as to whether we can use these things for OLEDs, and the answer I give them is no. We're kind of at the hairy edge of what can be made, what will form diamonds versus start abstracting hydrogens or just going to crap. And I hope to know within 6 months whether we're there or whether we'll be able to get there. Otherwise, there are just tons of other applications where these things just work cleanly. Yeah.
Along that line, could you use a cleavable tether holding those two things?
I thought about that, and I think you could. You'd have to make sure that that cleavable tether, okay, doesn't give rise to any groups that are reactive with your 19, with your 19 electron species. So it can't be oxidized, it can't be acidic. So what do you have in mind?
Silicon might work.
A silicon-silicon bond.
Or a silicon carbon one. Those can be cleaved by fluoride anyway. You get fluorides at the end. I don't know if that's a problem, but
We can look. We can look. We have to figure out how to put it together. Yeah, but that's something that's a possibility.
Other questions from the room? All right, well, thank you very much, Seth.